Hello again, physics friends. I am actually very excited about this topic because for the first time, we're going to actually be able to specify what superposition is instead of just what it is not. So far, we have been restricted to saying things like, in the two-slit experiment, a quanton does not take slit 1 or slit 2 or neither or both. It takes a superposition of both slits. But we haven't really had an understanding of what superposition actually means in this context, okay? Similarly, with our hardness interferometer, we have been restricted to saying that if an electron enters the hardness box and exits the merger box, then we can say that that electron made it out of the interferometer, but we can't say that it took the H path. It didn't take the hard path, it didn't take the soft path, it didn't take both, and it didn't take neither. We just say that it took a quote-unquote superposition of both paths. And again, we didn't really have a clear definition of superposition. Now, one of the kind of hallmarks of this course is that we have only introduced mathematics as needed to clarify a situation. And we are now arriving at a place where in order to have a clear, crisp, and well-defined explanation for superposition, we need to have some mathematical framework. Okay, and that's what we're going to do. Because the last thing I want is for you to walk away from this course thinking that in quantum mechanics, physicists are waving their hands and saying superposition without having a clear picture of what that is. In fact, there's a very clear and well-defined mathematical understanding and definition for what it means for a particle or a quanton to be in a superposition state. And the exciting thing is today we get to see and use that framework. So I'd like to start by coming back to our friend the color box. And when we've had the color box in the past, we've talked about an electron at the input, and then we've said the electron could exit either the blue or the white port. Never both, only one. And we're guaranteed that the electron will come out of one of those two ports unless one of them is blocked. But if the color box is unblocked, then one electron comes in and one electron comes out. Now, I'm going to introduce a very similar notation as a way to describe the input and output states of this color box. And at first sight, it doesn't look any different, right? So here's the color box. We have an input, a white output, and a blue output. And the notation I'm using here is this symbol, which is a vertical bar, and then a label, N or B or W, and then a little angle bracket, okay? And this quantity, this whole object here, we're going to call a ket. And ket is the last part of bracket. And what we'll see in the future is that we can have a bra, which is kind of a mirrored version of the ket, and we can tack it on to a ket, and we're going to see that this quantity, bra ket, represents something called an amplitude, which is related to the probability of an outcome. And just as a preview, if you start with a system in state B, indicated by the ket B, and you want to know the probability that it will be measured in state A, then the probability is given by the magnitude of A and AB, that bra ket, squared. So this term is an amplitude and this term is a probability. And today we're going to define this a little more to understand what is meant by an amplitude and what this notation of bra and ket means. For now, we're going to put all of this aside and just focus on these kets. And the main idea is that a ket is a visual object that represents the state of the system. So for example, in the color box here, we have an electron at the input, and we can represent that state as the input ket. After going through the color box, if it comes out the blue port, that electron is now in the blue state, so it has a ket with a B in it. And if it exits the white port, it has a W ket, meaning that the electron is in the white state. Now, given that for color boxes, we already basically used the same labels, this doesn't seem like much of a win to put the angle brackets and the bar on it. Let's see what happens, though, when we talk about a Stern-Gerlach experiment. So in that case, we might have a Stern-Gerlach analyzer oriented in the z direction, in which we inject silver atoms in some unspecified input state, and they're going to emerge from the plus port or the minus port. If they emerge from the plus port, those atoms are now in a state mz of plus, and if they emerge from the minus port, their state is mz minus. Okay? We can represent that schematically in the following way. We can take the same box and just say the input state is the inket, and the two output states are plus and minus, and we also have to specify the direction that the measurement was made in, right? So the z subscript here is representing the fact that the atom exiting the plus port is in the state plus in the z direction, which is like saying it's plus in the mz value is plus. Or here at the exit in the minus port, the atom has a state minus in the z direction, which is like saying mz is minus mb. So this is just a cleaner, more compact way of writing things. And what we're going to see is it becomes really, really useful when we talk about what it means to be in a superposition state. Incidentally, this notation is called bracket notation because it forms, you can form these bracket quantities, as we alluded to before. It's also called Dirac notation, after Paul Dirac, who is one of the great minds in the world of quantum mechanics and who made significant contributions to the field. He was also a rather curious character. You should look him up and read some of the stories about him. Some of them are pretty wild. Now, at this point, you still might not be convinced that this added notation is useful or even a good thing. So let's actually put this to use in a way that we can understand more clearly why this is going to be a win for us. So let's think back to some of the experiments that we've seen before. Here's one. We have a hardness box followed by a color box. And if you remember, we found that if you shoot a bunch of atoms, or I guess in this case electrons, into the system, let's say we found 100 electrons came out of the S port, the soft port of the hardness box. If that was true, because we know then that a soft electron has no color, or is in a state of unspecified color, that means that we would have some electrons coming out the blue port and some out the white port. And for hardness and color measurements, we found that that probability was going to be 50-50, okay? We also saw something similar when we looked at the Stern-Gerlach analyzers, okay? So if we start here with a SGA oriented in the Z direction, and we follow that up with a Stern-Gerlach analyzer oriented in the X direction, and we find, let's say, 100 silver atoms exiting the plus port of the first analyzer, we then found that we would also have a 50-50 probability that each of those atoms would exit the plus and the minus port of the X analyzer. Okay, so what we found in these cases is that a quanton with a defined hardness had no defined color and equal odds of coming out of the blue and white ports. And a quanton that had a defined Z orientation had no defined X orientation and therefore had a 50-50 probability of coming out the plus or the minus port. But we have to remember that the probabilities are not always going to be 50-50 when you have an atom in an undefined state. So for example, if we have, say, an SGA Z measurement followed by an SGA 10-degree measurement, and let's say we have 100 atoms exiting the plus port of the Z, it is not going to be the case that we have equal odds, 50-50 odds of coming out of the second analyzer, right? So it is not correct to say here that we would get 50-50, right? That's not true. In other words, an undefined, so an atom in a defined Z orientation does not have a defined orientation in the 10-degree direction, but undefined does not equate always to 50-50. In fact, we know that the probability of exiting this plus port is given by the square of the cosine of 10 degrees over 2, and when you do that math out, you find that it's about 97% odds of coming out the plus port, which leaves you with 3% odds of coming out the minus port. So undefined does not mean even odds. So we need a way to to specify this state in a way that quantifies the probabilities for the following measurement. Okay, so the state here is a plus in the z direction in both cases. Okay, so we could write the state here. Every atom exiting the z analyzer is in the plus z state. Okay, and here also these atoms are in the plus z state. But we'd like to also write these in terms of plus and minus x. Okay, and I've put these kind of underlines here as a placeholder for a coefficient that will specify how much x state do we have, how much plus x state do we have, and how much minus x state do we have. In other words, what is the probability that an atom in the z state would be measured plus x versus minus x? And it turns out that the numbers that we're going to put in here are not the probabilities themselves, but they're something called amplitudes. So A and B are so-called probability amplitudes. And the difference between a probability and an amplitude is that the magnitude of the amplitude squared gives you the probability. In this case, since A is the coefficient of the plus x state, the magnitude squared of A gives you the probability of exiting the plus port of an X analyzer. And likewise, magnitude B squared is the probability of exiting the minus port of the X analyzer. Okay. Now it wouldn't make much sense to write the Z state in the second experiment in terms of the X plus X and the plus X and minus X states, because we don't have an X analyzer here, right? We have a 10-degree analyzer. So what we'd like to do in this case is express the plus Z state in terms of the quantities that we're going to be measuring. And the quantity that we're measuring is a 10-degree. So if the atom comes out of the plus port of the 10-degree analyzer, then it would be in the plus 10-degree state. And if it comes out of the minus port, it's in the minus 10-degree state. So we would like to write the state of the atom upon entry to this SGA-10. We'd like to write it in terms of these state vectors, in terms of these state kets. So we want to write it as something times plus in the 10-degree direction, plus another value times the minus in the 10-degree direction. Okay? And so what can we put there? Well, we can put numbers here. And I'll put for now C and D because A and B were already used before. And what we know here is that the magnitude squared of C has to be 0.97 because we have a 97% probability of coming out the plus port. And likewise, the magnitude of D squared is equal to 0.03 because we have a 3% probability of coming out the minus port. So it's worthwhile taking a quick mathematical aside about the meaning of a magnitude. So we see the symbol vertical bar squared. That reads the square of the magnitude of the quantity that's inside of the 3-dot quantity. So for example, the magnitude squared of A is the square of the magnitude of that value A. Okay, so here this magnitude term means take the magnitude of. So, for example, the magnitude of 15 is just 15. The magnitude of minus 15 is plus 15. Okay. In general, though, our terms like the A and the B and the C and the D that we saw on the previous slide, those can be complex numbers in general. Okay, so complex numbers meaning it involves the term I, which is the square root of -1. That's an imaginary number. And if you have a number that is a combination of a real number and an imaginary number, in general, we call that a complex number. Now, we'll come back to complex numbers in the future as needed, but for now, I just want to point out that these magnitudes allow you to get a real number, a real positive quantity, even if the term in the brackets, the term in the vertical bars, in the magnitude setup, is a complex number. You can still get a positive real quantity out of it. The claim then, right, is that the magnitude squared of A gives us the probability. So it is entirely sensible that this is going to be a real number, and in particular, it's got to be a number that's between 0 and 1, because you can't have a negative probability and you can't have a probability bigger than 100%. So let's come back to this experiment where we have a Z analyzer followed by an X analyzer, and we've identified that the atoms in this intermediate position are in the plus Z state, which we can write as a superposition of plus X and minus X states. I want to look at that statement again. Okay, so if we call this the intermediate state here, okay, we can say the intermediate state is given as some amplitude A for being in the plus X orientation plus some other amplitude for being in the minus X orientation. And we know that the probability of being measured plus X is mag A squared. And we know that the probability of being measured minus X is mag B squared. Okay. So we have the following. We have mag A squared is a probability of exiting, as stated before, of exiting the plus port of the SGA X, and mag B squared is a probability of exiting the minus port of the SGA X. Okay. Now, if we think about that for a minute, we know that the total probability is 100%, and the total probability of exiting that SGAX is given by the sum of the probabilities of exiting either one port. So we know that when we add these two quantities together, we better get 1 for 100%. Okay, that's a given. So that is allows us to solve for A or B given the other. Like if we know A, we can find B, and if we know B, we can find A. The other item that I wanted to point out explicitly is that this term A is given a special name. It's called a probability amplitude, not a probability, but a probability amplitude, okay, of exiting the plus port of the SGAX. And similarly, B is the probability amplitude of exiting the minus port. So the coefficients in the state, the A and B, those are probability amplitudes. And they're related to, but different from, the probabilities themselves. The probabilities are the magnitude squared of the amplitudes. Okay. Now here we know something about what A and B have to be, because we know that mag A squared has to be 0.5, and we know that mag B squared has to be 0.5. Okay. So we have a few options for what A could be. Remember, 0.5 is 1/2, 1/2. So that tells us that the magnitude of A is got to be 1/√2. And likewise, the magnitude of B is also going to be 1/√2, right? Remember, the magnitude is a positive quantity. But that means that there are many values that A could take, right? A could be 1/√2, or it could be minus 1/√2 because the magnitude of both of those is 1 over root 2. But it could also be, it turns out, I over root 2, in other words, the square root of minus 1 over root 2, or it could be minus that. And it turns out that there are even more options than that. It could also be e to the I alpha over root 2, where alpha is any real number. Or it could be minus that quantity. So there's actually an infinite number of values that you could assign to A that would give you the correct probabilities. So if you only knew the probability was 50%, then any one of these would work for you. Okay. Now, if you don't know or are not familiar with imaginary numbers and I, that's fine. Don't worry about it for now. In fact, we're going to simplify our lives for the moment and just describe the state as 1 over root 2 for both A and B. So we can write the following. We can write the intermediate state as 1 over root 2 for plus x and 1 over root 2 for minus x. And given the information that we have so far, this description is fully consistent with the outcome of 50-50 probabilities. Now, if we come to our other experiment, where we have SGAZ followed by an SGA oriented at 10 degrees, we still have this intermediate state, which is plus in the z direction, but that cannot be 1 over root 2 plus 10 and 1 over root 2 minus 10, right? Because the probabilities are not 50-50. So how might we write this down? We could say that this intermediate state, which is plus in the z direction, that's our intermediate state. We could also write as the square root of 0.97 in the plus 10 state and the square root of 0.03 in the minus 10 degree state. Okay? And if we compare that with the following, the intermediate state is 1 over root 2 plus x and 1 over root 2, in the minus x direction. These two states are the same, right? Because they both describe an atom that has just exited the plus port of a Z analyzer. These are both the same state plus Z, but we've written them in what we call different bases. In the first case, we've used the 10 degree orientation basis. In the second, we've used the x direction as our basis. Okay. We can also see that the probabilities of being measured in the 10 degree plus is 97%, whereas in the x direction plus, it's 1/2. So this is the really nice thing. Both of these are superposition states. So the first one, this whole state, is a superposition state for a measurement of the magnetic alignment in the 10 degree. This is a superposition state for a measurement in the x direction. But notice it is also a pure state or a defined state or a definite state. Definite, wow, I really need to work on my spelling. It's a definite state of mz. In other words, it's plus in the z direction, 100%. Okay. And so we see that we can write a given state as a superposition of other states. Both of these are superposition states, but they have different probabilities for the outcomes in the 10 degree direction versus in the x direction. We have more to say about Dirac notation and Bras and Ketz, and we'll come back to that in subsequent videos. But I'm going to pause here and let you digest this for a bit. And until next time, be well and stay safe.